And the next paper here is going to be on subgoal graphs for optimal pathfinding in 8 neighbor grids by Tansel, Uras, Sven König, and Carlos Hernandez. And it's Tansel who is presenting now.
Thank you. So today I'm going to talk about subgoal graphs, which can be used to find optimal paths in 8 neighbor grid worlds. So I'll just start by defining the pathfinding problem, which we all probably know very well. The environment is split into grid cells. A cell is either blocked or unblocked, and an agent moves from its current position to one of its neighboring positions, one of its neighboring unblocked positions, and we want to find the shortest path between any given start and goal positions. So this kind of formulation for pathfinding is used very often in pathfinding games or video games for pathfinding for agents. And it can be an expensive process, especially if you want to do it optimally. So basically, there is often time to pre-process the maps so that the search online is much faster. We can do it before a game is released or while a map is loading. So last year, there was a competition whose subject was this, and I want to give the details of the competition here rather than in the experimental results because I think it highlights our design goals well here. So there's an offline phase and an online phase. And in the offline phase, we are given the map, but we don't know which problems will be asked. And we are given 30 minutes of pre-processing time. We are allowed to store as much data as we want. And then we go to the online phase where we are given the problems, and we try to find shortest paths or as good paths as possible. So there are 3 evaluation criteria here. We want to find high-quality paths. We want to find the paths fairly quickly, and we want to use as little memory as possible. So our approach to this is subgoal graphs. So we want our subgoal graphs to be optimal, and we want to strike a good balance between runtime and memory. And today I'm going to talk about 2 variants of it, simple subgoal graphs and 2-level subgoal graphs. So the inspiration for subgoal graphs is visibility graphs. So I will just describe visibility graphs here for a while. Visibility graphs don't work in grid world. They're in continuous environments, and they use polygonal obstacles. And given the start and a goal cell, we build a visibility graph where the vertices of the graph is the start and the goal cell, plus all the corners of the obstacles, and then we connect every vertex that are visible from one another. And then searching over this graph will yield an optimal path in the actual environment. So why do we want visibility graphs? Which properties of it help us? It is optimal, that's something we want. And it only considers the corners, and this helps us avoid looking at all the cells in the grid. And it is very trivial to follow the edges in visibility graphs, you just follow the line. In grids, it will not be the case, but we will try to emulate this. And also, most importantly, most of this graph can be constructed offline and stored. If you don't know the start and goal state, we can just link the corners. And then once we know the start and goal state, we can add it to the graph and search it. And the bad thing about visibility graphs is they usually have notoriously high branching factors. So there are 2 main themes in this talk. The first one is how do we translate visibility graphs into grid worlds, and this part will be covered in simple subgoal graph parts. And the second theme is how can we ignore parts of the graph during search without losing optimality, and this will be in the 2-level subgoal graph part. Apart from these 2 subgoal graphs, I'll mention 2 methods of improving this further briefly. And then I'll give experimental results, including some results from the competition. So this is a simple subgoal graph. It looks like a lot like a visibility graph. Basically, like in visibility graphs, we place subgoals at the corners, and then we connect them, store this graph, and in the online phase, we connect start and goal to the graph, find a path over this graph, and this will be our high-level path. And from this high-level path, we find a low-level path by following the subgoals on the path. So one thing I haven't specified here is what is our connection strategy. And that's something that I'm going to mention later. First, I'll give some quick preliminaries. So we are in 8 neighbor grids. We can move in 8 different directions. Cardinal directions cost 1, diagonal directions cost square root of 2. and obstacles block movement, and there's one special rule where we can't move diagonally if one of its associated cardinal directions is blocked. So in here, this single obstacle blocks 3 movements of the agent. So with these movement rules and movement costs, the optimal way of going around obstacles is by using its corners. So that's where we place the subgoals, A, B, and C here. So if we had allowed the movement shown here with the red arrow, then we wouldn't be placing a subgoal at A, but we would be placing it in the 2 cells that the arrow connects. And in 8 neighbor grids, we use the octile distance heuristic. It assumes that there are no obstacles in the environment and just computes the shortest path between 2 cells by just comparing their x and y coordinates. And it does this by computing exactly how many cardinal and how many diagonal moves it must make. And in this case, it's 2 cardinal and 3 diagonal moves, and no matter in which order it does that, it takes them from S to G, assuming there are no obstacles. So back to our question of which subgoals to connect. We want 3 properties. The first one is we want to be able to find optimal paths. The second one is we want a low branching factor, as low as we can get. And the third one is we want to find the low-level path fairly quickly after we have found the high-level path. So I'm going to build up to the definition that we use. I'll start with this definition of H-reachability, which is something we came up with. Basically, we say that 2 cells are H-reachable if and only if there's a path on the grid whose length is equal to the heuristic cost. So this definition is very similar to visibility, actually. When you think about it, in visibility graphs, you use the Euclidean distance, and there's a path of Euclidean distance between 2 cells if and only if they are visible from one another. So back to the grids, we can rephrase the definition of H-reachability as this. There's a combination of C cardinal and D diagonal moves connecting the two cells that are obstacle-free. So this is kind of a setup for the next definition, which is safe H-reachability. Safe reachability requires all combinations of C cardinal and D diagonal moves to be obstacle-free. So in this case, this area shown by the arrows. And our third and last definition is direct H-reachability. It's basically safe H-reachability, but we also don't want any subgoals to be on this area. So it turns out that connecting all the direct H-reachable subgoals is necessary, and it is sufficient for optimality. The proof is in the paper. I'm not going to talk about it. We have a better branching factor than visibility graphs, and that's because any direct H-reachable edge is also a visible edge. There's a quick visual proof here. The red line is the visible edge, so it must fall in that parallelogram area. And third, it is very quick. It's very trivial to follow these edges because you just basically move in that direction. You know exactly how many moves you must make in which direction, and no matter which order you do them in, you are safe to be obstacle-free. So we place subgoals at corners, we connect direct H-reachable cells, and now we have our simple subgoal graph. We store this, and during runtime, we are given the start and goal states. So the first thing we do is we completely ignore the simple subgoal graph and try to find a direct path between start and goal with the heuristic cost. We only try a single trajectory between them. And if we have found a path, then that's the optimal path, and we return it. If we couldn't find a path, then we verify that start and goal are not direct H-reachable, and this is for the proof, actually. Next, if we couldn't find a quick path between them, we connect start and goal to the graph by using direct H-reachable edges. And then we search over the graph to find the shortest path on this graph. This is the high-level path, and then we find the low-level path by following this high-level path, following the subgoals on this high-level path. So I also want to mention something about identifying all the direct H-reachable subgoals from a given cell. This is a problem we encounter both in construction of the graph and during runtime. when we're connecting start and goal. We want this to be very fast, and the way we do it is we basically explore the direct H-reachable area around the given cell and collect all the subgoals in that area. And we have a faster method of doing this by using clearances. Basically, we pre-compute and store clearances in 4 cardinal directions. And a clearance means how many moves you can make in a direction without finding a subgoal or without hitting an obstacle. So with these clearances, we can only look at the clearance values of these black cells that you see on this board and find out all the direct H-reachable subgoals. So that's it for the simple subgoal graphs. So I'm going to talk about two-level subgoal graphs now. And I'll start by pointing out what's wrong with simple subgoal graphs. So in simple subgoal graphs, we put subgoals at every corner, and if we have a weird-looking wall or even a diagonal wall, we'll be having a lot of subgoals. And these subgoals are not useful for most of the time. They're only useful for connecting a handful of instances. But whenever a search explores this area, they're expanded, and it's a waste of time for the most part. And the two-level subgoal graph addresses this issue. This is actually not a specific method for simple subgoal graph or even for grids. It can, I assume, can be used for any graph problem, but I haven't had an idea of where to use it other than here for now. And basic idea is we partition the subgoals into global and local subgoals. The global subgoals are shown in blue, and the local subgoals are the red ones. And during search, we can safely ignore all the local subgoals that are not directly connected to the start or the goal. So here's an abstract representation of the two-level subgoal graphs. The local subgoals are only used to connect to the global subgoal graph. And local subgoals can only appear at the beginning, at the very beginning, or at the very end of the paths. So two-level subgoal graphs have 2 properties that need to be satisfied. The first one is required for optimality, and that is all of the subgoals must be optimally connected through global subgoals. And the second property is now we are allowed to use H-reachable edges as well. So actually, I forgot to mention in here, this doesn't show the whole picture. We have more edges, actually. We have all the edges of the simple subgoal graph, but we just don't consider them until the relevant local subgoal becomes part of the graph. So I will skip the construction of two-level subgoal graph part. It's detailed in the paper. So this is the two-level subgoal graph we obtained from the simple subgoal graph in the previous example. It satisfies both of those properties. And briefly, the way we construct them is we start with the simple subgoal graph, assume all of the nodes are global, all of the subgoals are global subgoals, and at that point, the 2 properties are satisfied. And then we greedily try to mark some subgoals as local, and we are allowed to add new H-reachable edges. So in here, for instance, A and D are connected through C. So if we hadn't added the edge between A and C, then A and D would be connected through B and C, but since B is not local, that would violate the property. And since it's a greedy approach, we don't always end up with the same two-level subgoal graph. We can end up with different two-level subgoal graphs, and we don't have any guarantees for the minimum number of subgoals. Using the two-level subgoal graph is very similar to the simple subgoal graphs. We connect start and goal to the graph with the direct H-reachable edges. And also for all the local subgoals that are connected to the start and goal, we add them into the graph by using the edges that we have stored. And then we simply proceed as in the simple subgoal graph. So this is just one example of how much smaller of a graph that we are allowed to search by using two-level subgoal graphs. This has a lot of weird-looking walls, and it's very efficient here. And also in this case, you can see that there are hexagons, and they are cleared of all the unnecessary subgoals and edges in the two-level subgoal graph. Okay, so I'm going to talk about 2 additional improvements on two-level subgoal graphs. The first one is the discarding of local edges between local subgoals, yeah. So this was the image that I shown earlier, and it's not the complete picture. We can have connections, like we can connect start and goal through a single common local subgoal or through two local subgoals. And it turns out that a local-to-local edge is only used in this case. So it's a very small portion of the whole possible set of instances. Okay. Also, on most of the on some cases, the local-to-local edges can make up to 70% of all the edges. So they waste a lot of memory, and they are being used very, very less. So we discard these edges, and optimality guarantee is lost, but in reality, the optimality hit is not that noticeable, and we also have some methods of mitigating this loss. Another improvement is we can, if we have a manageable number of global subgoals, we can simply compute the pairwise distances between all the global subgoals, and this will help us avoid doing search online. So now to the experimental results. I'm going to have this table up here. This compares A star versus simple subgoal graphs versus two-level subgoal graphs versus two-level subgoal graphs with pairwise distances. And the two-level variants have discarded local-to-local edges. I'll just highlight some of the interesting results here. And we are using all the maps in Nathan Sturtevant's benchmarks, which are available in this link. So the first and the best result we have is on mazes with corridor with 32, simple subgoal graphs is 675 times faster than A star. And this is not very surprising because when you think about it, if you double the corridor width, the number of subgoals remain the same, but the number of cells that A star has to expand is quadrupled. Also, on the same maps, it is 18 times much faster to compute the subgoal graph online and then do the search rather than do an A star search. In fact, this is the case in many of our benchmarks, and most notably it is the case in a game map, which is StarCraft. So this suggests that even if the environment is dynamic, simple subgoal graphs could be used. On the other hand, on random maps where there is not much structure to abuse, almost half of the cells are subgoals, so we are not doing so well here. So the two-level subgoal graphs gain the most. We gain the most from using two-level subgoal graphs on StarCraft maps, which contain a lot of diagonal walls. And it's 3.2 times faster than simple subgoal graphs and about 85 times faster than A star. And on the other hand, on Maze 32 maps, we're actually losing runtime with using two-level subgoal graphs because it doesn't prune much, but we now have to deal with H-reachable edges, which are harder to follow compared to direct H-reachable edges. And calculating the pairwise distances is usually almost always better as long as we have time and memory for it. On average, global subgoal graphs require very little memory, up to 2.5 megabytes, except for random maps where it requires 5 megabytes. And also pre-processing is pretty fast. It's no more than 100 milliseconds for simple subgoal graphs, and it's usually less than a second for two-level subgoal graphs, except on the StarCraft maps where it does a lot of work. So I'll quickly give some results from the competition. Our entry in the competition was two-level subgoal graphs with discarded local-to-local edges. And I'll just have this result from the competition. More can be found at this link. Our entry is circled in red. These show all the optimal planners for the game maps, in the game maps. And this compares the memory used versus the runtime used, and in here we are doing well. So in conclusion, it's actually pretty much what I said, and I'm running out of time, so thank you.